Yeah. And let me welcome the participants to this second talk of the second season of our optimization online seminar. So the speaker today is Jong-Shi from University of Southern California. It is 6:30 in the morning in California, and I'm very, very thankful to Jong-Shi for accepting to give a talk in the framework of our seminar. So of course, Jong-Shi is well known in our community. He has amazing reputation. I just want to say that he received some important prizes, and to mention the Jonathan Neumann Theory Prize he received last year, and before he received the George Dancing Prize and many other prizes. Yeah, he's a well-known personality in our area. An important aspect is the fact that since 2019, Jong-Shi is editor-in-chief of our flagship journal of sound optimization. So a huge reputation, one of the most important figures of our community. Jong-Shi, you have 50 minutes for your talk. Thank you. Thank you for accepting to talk in the seminar.
Thank you, Raju. And thank you, Soren. Thank you both for inviting me to give this talk. It's the first, as Raju said, this is my first time presenting at 6:30 a.m. I think during some part of the talk, some of you may feel that this is enough, and you're welcome to go back to bed. Okay. Anyway, seriously, I want to talk a little bit about some of my work in recent days, and this actually started a number of years ago. I'm starting to work on some so-called in quotes optimization problems. This is not the first time I use this word, but I think that this is really the class of optimization problems that we all should pay attention to. And also there's a feature of the non-problems that I address in this talk that are not exactly the same, because if you look at the literature, you see a lot of this kind of problems, but I do want to point out that there's one important feature that is missing in a lot of those papers that we try to capture in our work. And this feature is what makes this class of problems really challenging. Okay, so I should also point out that a lot of this work is joined with Dr. Cui Ying, and she may be here. And in particular, the monograph is written with her. So I thought I would start this by giving you some general thoughts about the old era, or the it's still going on era of the state of the field, in particular relevant to the field that we are all familiar with, machine learning. And then I thought I'll just make a sort of a readiness test, a kind of a light-hearted humor, to see whether you are on board, what you think about this era, or maybe you think that the present era, or maybe even the past era, is a better suited for you. So and then I start a bit more serious and talk about really the key non-features that I want to emphasize. And I want to show you, I mean, it's every one of these non-optimization problems that I give can very easily make a talk of its own. And these are problems that really require the kind of machineries that we're going to talk about in this work. Talking a little bit, introducing this monograph. Okay, so some general thoughts, right? So these are my personal thoughts, having been around for a while and then seeing what happened And especially nowadays, everyone is talking about machine learning, and to some extent, this term is fading away and replaced by artificial intelligence. But before we get there, everyone knows about the positive impact of machine learning. But I do want to talk a little bit about the negative impact, especially how it does to our own field, on the optimization field. And then sort of by way of this, sort of raise an alarm and sort of encourage the community to think beyond machine learning, because I think that there's much more in optimization than just machine learning. Okay, now can you see the top? Because my screen, the top is a little bit cut off. It's okay?
It's okay, it's okay.
Okay.
Go ahead.
So I want to talk about, I think that we are all very comfortable, very familiar with convexity and differentiability, right? So one of the two. So in a way, these two features are really the safe haven for us, and also for applications for decades, right? And in recent days, of course, becomes very popular in machine learning, and also probably going to be very popular also in artificial intelligence. But anyway, these are the two features that were sort of have become so safe, to the extent that people start modelers, right, who are not really familiar, not know enough about optimization, that they really sort of abuse, right? So for us who know the limitations and advantages of these two features, we use them with caution. However, I think that a lot of times when people do not know about the subject well, they start to routinely use these two properties to the extent that they sacrifice the realism for convenience, right? And for the modelers sort of sacrifice, they simplify the models in order to fit the paradigm. And then algorithm designers would do whatever to stay within this comfort zone, even at the expense of potentially wrong approach. I mean, they start to sort of use methods from convexity, differentiability without really, especially differentiability, right? They start to use whatever possible in order to stay with this comfort zone. And then after a while, practitioners, especially practitioners who really know nothing about optimization, they are content with what they were told, right, with the resulting models, algorithm, and solutions. I think that's very dangerous, right? So for people who know them, they not being very honest and forthcoming in sort of explaining the limitations of this. And then when things start to follow through, then the practitioners who don't really know the subject, then they will take whatever they get. And then after a while, this is what the result is, I think, is that the tools are being really abused. And then people, because they stay with this very comfortable zone, the advances in science will be stalled, right? And then I think what is the worst is that when they start to take whatever they get as their solutions, and they build a future based on this very soft ground. And I think that in the long run, if things are not corrected, then I think that ultimately it's like building a pyramid on a sort of a soft sand. And then maybe for the first few 100 feet or so, maybe it would be safe. But when you start to really build up to the top, then I think that when things crumble, then I think that it's very dangerous if one starts to build things based on soft ground. So now I want to sort of do this a little humorous thing, and then try to see whether you sort of think that this is an era that you're ready for it, or rather maybe you can sort of have better things to do, okay? So this is a little humor before the storm. So let's start with this question, right? So are you satisfied with this comfort zone of convexity and differentiability, right? So if the answer is yes, then you probably won't need this talk, right? Then you can sort of rest. You can, and then what you do is that you will live happily ever after. And I think that we all want to do this, right? So we all want to live, and then we take a shortcut, and then we are happy. On the other hand, if you want to be a little bit more challenged, and if your answer is no to that question, that you are not, you want to be challenged beyond these two themes, then the question is now, how do you deal with non-convexity and non-smoothness? This is the, if your answer is no to the first question, and now the question is, how do you deal with this not very friendly features? And of course, you have several ways you can do. You can take this way, you basically, you know that they are present, but you ignore them, right? And that's like what a lot of people in other community are doing. They basically ignore these properties, or they give them minimal treatment or even the wrong treatment, and they're happy, right? So they take this path, and eventually they also arrive at this happily ever after, and they very happy. Okay, so, but now if you are not, you want to take things a little bit more serious, then you start to look at some challenging problems, or maybe even some stylized problems, and there are many interesting ones, and not many interesting and many challenging ones. And then you deal with them, okay? You deal with them in the best way you can. And then after that, you stop. Okay, and then again, if you when you stop, you again live happily ever after. Okay, so you can take all these different paths, and eventually you can also live happily after. And so it depends on what you do. Okay, so at this point, when you are not satisfied and you want to go beyond stylized problems, then you can try to really start to deal with these non-properties in a faithful way. Right, so I'm not going to take shortcut, and then I'm going to really deal with them in a serious way. So faithfully deal with these non-properties. Okay, so what do you do? Well, you know that you're going to deal with these non-properties faithfully, and then of course, what you could do is that you can look at heuristics and start to do more heuristics, and eventually you're going to build heuristics on heuristics, and then what's going to happen, I don't know, right? So when you have simple models, you can use heuristics, no problem. But when you start to build complex models on those simple models, and if you start with heuristics, then basically you end up building heuristics on those more complex and more realistic models. And what's going to happen at that time, I don't know. But still, for the modeler or the algorithmic designer, after they've done this, they're happy, and again, they live happily ever after. So all these paths will lead to this, which is very good. So now, again, so you don't want to take just do heuristics, and you do a little bit even more rigorous. And then now you come to take this hard road. Okay, you come to take this hard road. You want to strive for rigor, okay, so you want to have things done rigorously, but at the same time, you don't want to sacrifice practice. You realize what the practice requires, but again, you strive for the best you can in a rigorous way, so that you won't building heuristics on heuristics. So you start to take this hard road, and then you strive for rigor, and then you, at the same time, you also advance fundamental knowledge, and also prepare for the future. And hopefully the future will be more solid when you take this path. Okay, come down here. But where do you end up? I don't know, right? Maybe whether you will come back here, whether there should be a line that you back here, or maybe not. I don't know. So this is a question mark. And so basically, this is a kind of a dissection of the present state of our field. Okay, and then I think it all depends on which path you take. If you take this long path, where it leads to, I cannot tell you. But if you take the other part, I can tell you that you will live very happily. So now you take your choice, right? For me, I sort of want to live a challenging life to the best I can. So I take this path that will lead to question mark. What's going to happen? I don't know, right? Am I happy? I don't know, right? So everything. So I'm going to take this path, and then what you will, it's up to you which path you can take. Okay, you want to take. Anyway, so this is just a little bit of a humor about this new era. So what do I mean by non-problems, right? So there's actually a word features up there, Radu. Do you see that?
Yes.
You do, okay. So because that word does not show up on my
So I see non-problems and?
But do you see something above non-problems?
No, I don't see.
Ah, okay. So that's what I meant, right? So there's actually a word above non-problems.
Okay.
So I'll show you, right? See, there's a word features. Okay. And that's why I don't want to use full screen. Well, you haven't missed much in the past slides, but this let me not use full screen, okay, Radu?
Okay, good.
So that you won't. Okay. So so what are the features in what I would call non-problems actually? So actually, when I send this, I was saying that a lot of this, what we're doing now is really built on the work of Terry Rockefeller and Roger Wetz on their sort of. And so when I send the title and abstract to them, and then saying that this is really a tribute, dedication to what they have done, and he raised the question where I should put the quotes on the word non, okay? And what you see now is that the way I put the non is around the non itself. And another way you could do, presumably, correct me that I think the quote should be around non. The whole thing in quotes, non-problems. Terry, of course, is a very serious researcher, and he suggests that I should do things correctly and on around the quotes around non and not around non-problems. Okay, so anyway, what are the non-features? Well, we already talked about non-smooth, non-convex, right? And non-deterministic problems, that means the problems under uncertainty. Well, see, I cannot say under uncertainty using non, right? So because I want to put everything under non, and so I'll use the word non-deterministic, meaning this really is problems with uncertainty. Stochastic
we have a question. We have a question
yes.
in the chat.
Okay, so, good.
So
yes.
Wilfredo Souza is asking, what about the non-parametric models?
Well, okay, that's a lot. See, this is under here.
Okay.
See? Very good. I haven't missed things. Okay, it's just not apparent. And then non-parametric really is more. Yeah, you're certain right, but that I have not. Okay, so did I answer the question? Is here. I cannot fit a nice diagram, and you have to know that I didn't draw this diagram. Ying draw this diagram, and you should blame her, right? So tell me all the non, and then whether you can fit in a nice diagram like this, right? So this is one way that I can show you something which is reasonably nice. And then of course you can put many more, and then now how do you make this into a nice diagram, okay? So that's part of the answer why you see a lot of non-things that are not in this diagram. Also bear in mind that I also want to have all these non-things, but then I also want to fit them in a nice way. Okay, any other questions? No. Yeah, I'm sure that you can think about many other non-things. But these are the kind of non-things that I deal with a lot. And you can add that on, and maybe you can expand this figure and make them into something, gee, I don't know, make them like a, I mean, you can do it with your imagination. But the key feature here, at least as far as a very limited way of looking at this, is that these features are not decoupled. That's the key word, okay? Is that these features are coupled together. And mathematically, this is already very challenging. If you have a problem where you have non-smoothness embedded in non-convexity or mixed with non-convexity, and with uncertainty, all these things are coupled together and so that they become non-separable, I think that's already a lot of that's already very difficult, okay? And then you can also branch out. Non-stylistic means that I do not stop with specific applications. Although I must say that a lot of the research, a lot of these problems are really motivated by stylistic problems, okay? The stylistic problems give rise to non-stylistic research. That's really what this means, is that we need applications to motivate us to look at some of the general problems, some of the general mathematical and computational problems. But as I said before, we should not stop with them. And that's the non-stylistic part, meaning that we do start with stylistic problems, but we do not stop at them. Non-interpreting, meaning that I think that it's important for us as optimizers not just to talk to optimizers. We need to talk to people in applied areas and find out how this kind of non-problems arise and actually interact with them. Okay, so that's the non-interpreting part. Okay? Now, to a large extent, these two at the bottom are really for the students, right? Because I think that for the young people, I think that it's important that if you want to advance the science, I think that not stopping at sort of stylistic applications, we cannot do that. We need to push forward and try to derive some general principles. Okay, so you can add your own topics, you can add your own non-topics and make this expand from this diagram. So now I want to give you some examples, okay? I want to watch out for my time. Okay, so I want to, if I have time, I will talk all about them. First, I want to talk about structured learning. Structured learning is a fancy term for statistical learning, statistical estimation, or machine learning. So we call it structured learning as sort of a little bit fancier. So I'll start with this problem, okay? Now, everyone is familiar with affine regression, okay? Least square affine regression, for example, okay? But I wonder how many of you actually are familiar with the so-called piecewise affine regression, okay? Now, piecewise affine regression really means that the statistical model that you are trying to estimate is no longer a linear function, no longer an affine function, but rather is a piecewise affine function, okay? So what I'm trying to do is that you give a number of pieces. Now you can ask the question about K1, K2 here, but for the moment, let's say that K1 and K2 are fixed. And I can tell you more about K1, K2 later, but then for the time being, this is a piecewise linear, a piecewise affine model. This is the underlying statistical model. Okay, it's piecewise affine function, and you do a least square estimation of that. So you want to determine the coefficients to minimize the least square error. Okay. Now I'm not sure. I don't know how many of you actually have encountered this sort of estimate. This is definitely an extension of the classical affine regression, where you use your underlying statistical model is piecewise affine. And we actually have a paper on this. And a lot of times, if you try to fit, for example, the letter M, okay, which has several linear pieces, why restrict yourself to just a linear estimation? You know that you're not going to get very good estimate. On the other hand, if you allow yourself to use piecewise affine functions, then you're going to get better. Anyway, so this is a simple example where you see non-convexity, max minus max, non-differentiability, max minus max, and then these two features are embedded in the square. Okay, and so this is a very simple example of coupled non-convexity and non-differentiability. And this is not an easy problem, okay? And it's not Clark regular, for example, okay? So anyway, so I start with a pretty simple, but it's a very important problem. It goes beyond the classical paradigm of affine regression, where you see the non-convex and non-differentiability coupled together. Okay, some general comments. This is a convex quadratic function composed with a piecewise affine function. So it belongs to the class of piecewise linear quadratic function. Okay, so this class of functions is perhaps, besides the piecewise affine functions, this is probably the most friendly non-convex, non-differentiable class of functions. Piecewise linear quadratic is different from piecewise quadratic. It's, and there's some, okay. And this class of functions has the property that every stationary solution, directional stationary solution, is a local minimizer, okay? Now, this property, if you try to prove this, it's not difficult to prove this, but I don't think that you can find this result anywhere, okay? It's a pretty simple result to prove. If I tell you, once you are told that this is true, if you try to go ahead and prove it, you can prove it. But then again, it's not in any, I don't think that it's in anywhere. It has finitely many stationary values. Now, we try to do this on our own. It turns out that this finitely many stationary values, this result here, has much more general, in much more general context. And for example, Adrian Lewis has a paper on, I bet that most of you would not know this paper of Adrian, but actually it's about the more sought index problem or something. But that result actually gives to this special case, this is a special case of that general result. But again, I challenge you to try to prove this directly without citing that general result. This is not easy. Stationary values means that if you look at the directional stationary solution and look at the objective values corresponding to those, there are only finitely many. Okay, and then now algorithmically, you can actually compute a directional stationary solution by iterative convex programming base. Okay, so you can design an algorithm that will compute a directional stationary solution. So the problem is very stylistic, right? Of course, you say that this is very simple, it's very stylistic, but you can generalize it. And this is where I say that I don't stop with stylistic problems. You can look at this, okay? What is this? You have max minus max embedded in a convex, minus a convex, and embedded within which is max minus max. Try to design an iterative algorithm for computing a directional stationary solution for this kind of problems. I bet you it's not easy. If you have an easy way to compute a directional stationary solution for this kind of a function, let me know, okay? So anyway, so we start with something fairly simple, fairly stylistic, but we're able to generalize it to a much broader class of problems. Let me talk about another application. This has to do with, okay? You're probably all familiar with sparsity. This step function, the famous L0 function, is one if the parameter is not zero, and so on, okay? Now, you use this function to build a linear system, right? So this is just a linear system, but except that the variable here is not a continuous variable, but it's replaced by this L0 function. And we call this an affine sparsity constraint, okay? ASC, affine sparsity. Oh, I didn't write that here. It's called affine sparsity constraint, okay? Basically, you take a linear constraint, replace the continuous variable by the L0 function, okay? And this kind of a model, you can use this in the constraint or you can use it in objective. It allows you to model a lot of sparsity problems with logical conditions, okay? So the kind of L0 minimization problem that you've seen in literature to us is so simple and overbeaten, right? Now, this class of constraints, very, very challenging, okay? it allows you to model so-called strong and weak hierarchy, okay? Meaning that, for example, this would be one constraint, which says that if this constraint is 0, okay, another way of saying this is if this is 1, okay, if the left-hand side is 1, then the right-hand side must be 1. So that means that if you choose the j variable, then you must choose the k variable. Okay, so it's a hierarchy variable selection. This kind of a constraint can, of course, can be modeled using the different a's. And then if you use this to model this, you're going to end up with some coefficients here being negative. You also may have seen a lot of so-called cardinality constraints. Cardinality constraints basically corresponds to the case where the a's are all equal to 1. Okay, they are all equal. They're all equal, non-negative. And then you have an upper bound. So you choose a upper limit of the number of variables. So that's a cardinality constraint. And you've seen, again, a lot of papers on that. As soon as you allow the coefficients to be not equal, then what you get is so-called a cost-based variable selection, that there's a cost associated with the choice of a variable. This problem, cost-based variable selection, is like a knapsack constraint, okay? It's like in the OR literature, it is really an abstract, is really a knapsack constraint. Okay, now that kind of a cost-based variable selection, you don't find in the literature of statistics of machine learning. People just do not deal with that, okay, because it's hard, okay? So that's an example of this, okay? So this is a case where you can have negative coefficients, and this is a case where you can have multiple of this. And also group selection, okay? Group selection, you have certain groups of variables, and the choice have to be saying that if you choose one group, then some other groups have been chosen, and all the elements can be need to be chosen. All these are examples of logical sparsity. Okay, sparsity with logical conditions. They can all be modeled by this kind of constraint. How to deal with this is part of the non-research. So some general comments, this function, of course, is discrete in nature. And when the matrix A is non-negative, there are two ways to formulate an affine sparsity constraint. You can use complementarity constraints, or you can use integer variables using this kind of a big M formulation when you know that the original variables are bounded. Okay, so you have the soft formulation. Okay, so instead of putting them as hard constraints, you can put in the objective, and then this would be like some kind of you can think of either as a Lagrangian, you can think of it as a penalty, but it's a soft formulation of this. And now you end up with the objective function is with the L0 here, and then you have the plus function, which is the max of 0. And so you have this kind of function to deal with. And usually this is not so bad. And it is this kind of things that actually makes the couple, again, you have, I mean, this case is even worse, right? So this case, if you have the matrix A has negative entry, the constraints will not, the constraint here need not be even close, okay? Need not be, and we do have examples of that. And so when the matrix A has negative entries, the resulting constraint system, a affine sparsity constraint set, may not be closed, or may not be closed. And so therefore, the objective function here may not have a lower semi-continuous objective, okay? So now, I don't know how many of you are familiar with the term folded concave function. And I think of the folded concave function as you have the L0 function and you approximate it by something concave on one part and symmetrically concave on the other part. So you get a kind of a butterfly kind of function. And this is, in the statistics literature, this is called folded concave. And then if you approximate the L0 function by a folded concave function, and if they have it in the constraints, then you end up with constraints that are not differentiable, and they are not, if you approximate them by folded concave, then you end up with non-differentiable difference of convex constraint.
So we have a question.
Yes. Okay.
So it is a long question. So what I propose is, to answer this question after the talk. Yeah? So don't
Okay, I haven't seen
please
that.
ask your question. So we have it in the chat.
I have not looked at the.
Yeah, but.
Shall I go on?
Yeah, please go on.
Okay. So I want to talk about this other example. Okay. So now at this point in time, optimizers cannot beat machine learners in solving this problem when the sample size S is large. Okay. But I think that as a topic for rigorous study, I think that we need to pay attention to this. Okay. What this class of problem leads to is a multi-composite, non-convex, non-smooth, they all couple together, okay? Again, I take an easy square loss function, and the function f here is the composite of this. And then you can see this sort of a multi-layer thing. And this is the architecture structure of a deep neural network, right? So you have input, goes through a linear transformation, and goes through the so-called the ReLU function, which is really the max, the plus function, goes through a second layer, goes through different layers. So you have input layer, you have linear transformation, goes through the plus, go to the second. And so this becomes a multi-composite, non-convex problem. Okay? How do we deal with this using optimization tools in a rigorous way? Okay. So the idea here is exact penalization. We can actually penalize this, sort of pull out some of this, and actually look at this kind of so we pull out the individual constraints, and we don't use the L2 depenalization, we use an L1 penalization. So you basically pull out the layers one by one and put them into a form like this. Okay, so this is the penalty parameter, this is the last layer. So you end up with a kind of a constraint like this, where this function here can be piecewise linear, okay? And you penalize it so you have the absolute value, right? And now you need to deal with this kind. Now, in the piecewise linear thing, this is not too bad. This is piecewise affine, okay? And again, you can say something about stationary solution versus local minimizers for this class of objectives. You can have rigorous algorithms with supporting convergence theory, okay? Now, of course, the downside of this, because we strive for rigor, and so that the rigor comes with the expense, at the expense of solution efficiency when S is large, okay? And so that's the trade-off that we need to take, whether we want rigor versus something that is not so rigorous. The framework is nice, namely that this penalization framework, this pull out of this kind of, because it allows you to deal with what a lot of sort of the problems with under data perturbations, okay? So allows you, and then it also mathematically raises the question of what can we do with exact penalization. And then as we know that exact penalization have to do with error bounds. And so all these questions lead to the study of exact penalization and error bounds of non. Now I should mention that exact penalization for non-differential optimization problem, that's well studied in the optimization literature. But the theory of error bounds for non-differentiable optimization problem is not that well studied. We all know about the KL error bounds, but I can easily pose some questions for you about error bounds for non-differential optimization problem that is still fairly much outstanding. So some from some specific application, we're getting down to something pretty general. Okay, now I'm out of time because I do want to talk a little bit about the book, and then I can come back to talk. Maybe I should talk a little bit about this before I move on. So this is a new subject that I recently completed. This is about robustification of non-convex problems, okay? So you heard so much about robustification of convex problems, but then not so much about, so you start with a nonlinear program, and then I want to deal with all the constraints, put it in an equation form, okay? Now, if you want to look at the, in the robustification literature, you don't see this kind of equality constraints. And part of it is because if you require some condition like this, that this equation be satisfied for all perturbations, this is just cannot happen, okay? And also traditionally, the perturbation is that the objective perturbation and the constraint perturbation, usually they are separate. And so what we have developed is a general framework to deal with a joint robustification between among the constraints and objective, and also where you have equations. Okay, so the traditional way of dealing with this kind of constraint is just not possible. And the idea is very simple. We use value function. Okay, value function. So what this leads to is a value function optimization. You minimize an objective, and in the objective is the sum of a maybe nice function and a function that's a value function. Okay, it's the maximum over perturbations. And so anyway, so the idea here is that you have this. And there's also a distinction between pessimistic and optimistic formulation of a problem. So, and again, we deal with that separately. You can have pessimistic and then you can have optimistic way. But anyway, so the idea here is to point out that this is an example of a class of what we call a value function optimization. Okay, so you have game formulation, and then you end up with a problem like this, where the value function is a fairly complicated function. Okay. Okay, so I do have one last example here about so-called the familiar topic of C-bar. Okay, so you're probably all familiar with C-bar, conditional value at risk. And condition value of risk deal with one side, the right tail distribution. Okay, now because Mark is here, Mark, I haven't done the interval OCE, okay? Maybe I will do that, but anyway, so this is still about C-VAR. So instead of the condition values of risk, which models deal with one side, you can try to think about condition values of risk on an interval. So we call it interval condition value of risk, where the difference here is that this expectation is taken in an interval, okay? And the usual C-VAR is just one-sided, and now this is an interval C-VAR. If you write down this interval C-VAR, it becomes C-VAR minus C-VAR. C-VAR is convex minus C-VAR, so you're going to get a DC function. So this is an interval C-VAR. Recently, there's some study on the so-called buffer probability of exceedance, which is the first term, which is like the inverse of C-VAR, okay? And again, this is one-sided because it only talks about exceedance. You can similarly talk about decedence, which is the other way. And then in that case, one way to express this buffer probability of decedence is use the C-VAR. And then it ends up with some pretty interesting stochastic program, okay? So this is the buffer probability of interval, okay? So in the literature, you see buffer probability of exceedance, and now we extend it to intervals. And so you can bound this kind of probability by the probability of exceedance and probability of decedence. And then you end up with what we call the probability of buffer probability of intervals. If you look at the optimization of this, minimizing the C-VAR of a random functional, and this you can actually deal with, I want to show you this class of problem. You're going to end up with a value function minimized over this of a value function minus another value function, and the value function here involves expectation. Okay, so this is the class of, this is what you get when you deal with interval C-VAR. Okay. Anyway, enough about this, okay? So I'm going to skip the mathematics part because I don't have a lot of time. This is already 18, so I want to go directly to the book, okay? So this is a diagram that we have in the book, okay? You can see that a lot of different class of functions. You have DC, you have PC2, and then you have, I mean, this is certainly not exclusive, there's still plenty, okay? So you have semi-smooth, you have compositive, you have lower C2, and this diagram here sort of summarizes the relations between this different class of functions. And the reason this is important, you see PLQ here, piecewise linear quadratic. And you see here, the reason you see here, so Stan Yuryasev is not here, and he actually has this class of weak convex concave functions. and they also fit into this diagram. Anyway, so it's important to know this, the classes of functions, because they are the kind of functions that allow you to design algorithms, okay? So that's one thing that we will place a fairly much attention in the research, is that we want to be able not only to understand the theoretical part, but also to be able to design algorithms. Okay, so this what we end up with after maybe 2 years work is that we recently submitted to the publisher on a set day. Okay, and this is the title, and Dr. Chi-Ying is probably here. Okay, so the first two chapters, first one is mathematical persistence. The first two chapters are for students, okay? And it's good to put all these things together. And there are probably things that some people may not know, but again, for students, I think that this is a good review. Starting the third chapter, this is where the statistics, structured learning, biostatistics, and optimization. Now, this section here is fairly new, okay? So you have low randomness, and especially this is done in the context of shape optimization, okay? So you have shape constraints, but then you also have so-called either rank constraints, or there's also distinct constraints. For example, one example of this is that you want to say that you have, I want to choose no more than k vectors among n vectors, okay? No more than k vectors among n vectors. And you end up with this kind of a model, okay? So we discussed a little bit in this chapter. One thing that I want to point out is that I think that it's very important to think about a lot of the statistical estimation problem really from the perspective of composite functions. Do you see this slides well? Is it okay? Okay.
Yes.
Okay, so this chapter here motivates a lot of the later thing. It comes from statistics, okay? So statistics and optimization. And then chapter 4 is the beginning of the mathematics. You see all these classes of functions. You see subdifferential, second order direction, derivative, and so on. And then we have a full chapter on value functions, okay? So I've shown you some examples of value functions. And so starting from the basic ones, something that everyone knows, to something that's probably, this section here is interesting because we talk about the Denskin property for non-differentiable, sort of it goes beyond the well-known Denskin's property that many of you know, okay? It goes beyond that. And then of course, the stationarity theory, right? So we have a big section on piecewise linear quadratic programs. We have some second order theory. At this time, this second order theory is still fairly weak, okay? There's still a lot of things we don't know about second order optimality conditions when you have non-convexity and non-differentiability coupled, okay? And I can very easily give you examples where known theory of second order optimality conditions cannot be applied, okay? And then we have a whole chapter on algorithms. So how do we solve this? The key idea is surrogation, okay? Surrogation. You surrogate, you have a surrogation function upper bounding the original objective, and you optimize that surrogation function. And we have basic ones, and then we have advancements. A lot of this, so for example, we talk about BCD, block coordinate descent, and ADMM, and so on, okay? And then there's a whole chapter on error bounds, which are important, and you probably see this KL theory here. And then this is the more classical using local error bound to prove sequential convergence, and all these are for non-differentiable functions. And there are connections, and of course there are known connections between these two theories. And then linear regularity, which is a kind of error bounds for intersections of sets, it's very useful. Now, exact penalization is very useful because it allows you to extend a lot of things in this basic surrogation using exact penalization and do things with that. And then we have two chapters on specialized problems, non-convex stochastic programs, Okay, and you've seen some of that. I've shown you the integral CVAR, non-convex stochastogram, and the last chapter is on non-convex schemes. And so I think with this, I'll stop. I think that I'll cover almost everything. Everything is in a rush, and hopefully the book will come out next year. So with this, I'll stop.
So thank you very much, Jong-Shi, for the nice talk and for presenting your new book. So I think this is the right place to present such a book.
Yeah, hopefully people will. And again, as you see the picture, you can the diagram, you can decide where you are, whether you want to come down the hard way or you want to live happily after.
So we already have some questions in the chat, but I'd like to emphasize the fact that in this second season, we had 2 talks focusing on DC programming, which is a hot topic that we had last week, Amir Beck. And in your talk, DC programming played an important role.
Yeah, so, but we actually go beyond. For example, if you look at this class of functions that I showed in the beginning, that's not DC. You also need to be careful. Some class of problems, you can show that they are DC, but you cannot get their DC decomposition. And that's not useful when it comes to algorithm.
Indeed.
Okay. So where is that? So this one, right? This is not DC.
Yeah, indeed.
Okay, this is not DC. Yes. So DC, so for example, you haven't seen this. I should show you this. DC is a special case of what is known as implicit convex concave. I haven't defined it here, but again, this goes beyond DC. Okay, implicit convex concave. And an example is a stochastogram, what is known as a biparametrized stochastogram. Okay.
Yeah, indeed. But there is a hidden convexity which is when developing algorithms.
I know, but this is not hidden. It's implicit. This convex concave.
Okay. Yes.
Okay. It's not hidden. It's not hidden convexity. I know hidden convexity is very useful. I totally agree. Okay.
Okay. Let us take some questions. So, Dongley Do, please ask your question.
Okay. So let's see. I should stop. So let's see. Where should I see the questions?
No, but so I would like to ask. Dongley Do to. Oh yeah.
Hi. This is Dongley. Hi. How are you?
Good. Good.
I posted a question in the chat. Basically, I think to summarize it, simple. It's basically a non-smooth and non-convex problem have been studied in the discrete optimization for HND intensively. I'm just wondering, in terms of this non-problem you proposed, can you talk a little bit about the relationship between traditional discrete optimization?
It's very simple. I already said that, and I probably have not said it enough.
Oh, okay, yeah.
I have not said it enough. Okay, so this is where I want to find that word. The key is the coupled. When you have the 2 things coupled together, you cannot the traditional way. Where's that word? So if you look at this, okay, if you can tell me anything that you can deal with this is coupled. The key word is the word coupled. You have them coupled together, you cannot separate them. The literature, I will say that 90% of the literature, if not even 95% of the literature, when they talk about non-convex and non-differentiability, they are decoupled. And that's the easy part. The part where you have coupled non-convexity and non-differentiability is the hard part. And the literature has not dealt with this. And then a lot of problems are of this coupled kind. You have this, but then they are embedded within something which is, in this case, is differentiable. Okay, but if you go and look at some of the others, they are decoupled, they are coupled. Where's the word coupled? So to answer your question, the feature is in coupled non-convexity. That's the distinction. And that's the hardest. Where's the word coupled? I've used the word coupled non-convexity and non-differentiability. Did I answer your question?
Yeah, I think so, yeah.
You can look at this, okay? You have all these features. This is non-smooth, non-differentiable, non-convex, non-deterministic, meaning uncertainty, and they are coupled. They are non-separable. And that's a hard problem. And that's why this is where you need Rockefeller and West.
Okay. I see. So
Okay.
can I assume so this non-problem must be in the continuous domain, because when you go to discrete domain, by nature they are non-convex and non-smooth, right?
Correct. But then you need to be careful. And so discrete, I think that's a good question. Okay, it's a good question of how discreteness is related to non-convex and non-differentiable. I agree with you, okay? So you can look at discrete as non-convex, non-differentiable. Totally agree, okay? However, I think you need to be careful with their treatment. For example, if you look at this sparsity constraint here, okay, if you look at this, you can deal with it in two ways, okay? You can deal with it in complementarity, which is continuous, but of course related to discrete, but you can also deal with it as integer, which is the discrete side. Okay, so you have two different ways of looking at it, and there are connections, and you are certain right that integer discreteness is a type of non-convex, non-differentiable. Okay,
yeah.
But for example, think about this. If you, I look at this very simple problem. Okay, try to treat this using integer program. Okay, because you can formulate the max as integer program. You can formulate this as integer program. Try to deal with this in the integer programming methods. Okay, so you need to be careful. Yes, in a way that you could do things like this, but then it's a question of when you actually try to do it, how you're going to do it. You take this. Okay, it's a very specific. Yeah.
Thank you, Dong-Li. So let us take the question asked by Corina Averbul.
Okay.
So, would you like to ask a question? Otherwise, I can also read it. So the question was, are there some examples with time delays?
Oh, no. Okay. No, that's a different, one of my early life. Okay. One of my early lives, I dealt with differential variational inequalities with differential in this kind of problems. And then when you have that, then you can have time delays. And for example, I also work in transportation, and there are time delays everywhere. Unfortunately, my answer is that I don't have anything for that. And that is something that may be for volume 2. Is look at time delayed optimization, time delayed non-problems. So at this point, I apologize, I don't have anything, but it's certainly something that it probably can be reserved for volume 2.
Great. Xuan Guha Bai, who raised your hand. Please ask a question.
Yeah, thank you. Yeah, this is Zhonghua from the UK. I do have a question, actually 2 questions. So the first one is, do you have actually an example showing the dramatic consequence if a practitioner abuses the smooth solvers for these kind of non-problems?
No, I don't. Okay. So, okay. No, I don't. But then I think that you need to be a little bit careful. Okay. Now, if you look at a specific problem, okay, you're okay. Okay. I think the question is whether you agree or not with what I've written here. Okay. Now, if you're comfortable with this, again, as I said, if you're comfortable with the current methodology or current results, there's no need to use any of these things. Okay. But I guess the question is whether you are comfortable with this results here. Okay.
Yeah.
To say, right. So if you're comfortable with this, you said, oh, I don't care. I can continue to deal with this. I already have things that work well. No, I don't have sort of really bad things to show you what happened if you abuse. I mean, so I can show you things, for example, that a stationary solution, if you're not careful with the stationary solution, you really end up with solutions that have nothing to do with the minimizers. That I can do. Okay, but if you ask me whether I can show you that if a building is built on this heuristics and then it collapses, I cannot show you that.
Yeah, okay.
Right? But I can certainly show you that are the examples where you have stationary points.
Yeah.
and you are not careful with stationarity, then you end up with things that have nothing to do with minimizing. That I can show you. Okay. So, yeah. So you need to be careful what you mean by sort of what I can show you, because I cannot show you sort of really bad things, right? If you ask me whether they're really bad things, for example, a deep neural network that produces solutions, and how do I tell that it's really bad? I cannot tell you that.
Yeah, sure, fair enough. Yeah, thank you. So for the next question is like for this kind of a new type, like to me, it's a new type of problems. It's called non-optimization. So for this collection of problems, is it possible maybe in the future to develop a general solver for this whole class of problems? Just
yes
like the
no.
nonlinear solvers.
Yes and no. Okay, yes and no. I think if you ask me at the present time, okay, I think there's still a lot of things we need to learn. Okay, and so if you ask me in the next few years, I will start looking at stylized problems and build them up to the point where I'm comfortable with some general things. Then I can start to build general solvers. For example, if you now want, if you ask me whether I can build a solver, general solver for this kind of piecewise affine regression, my answer is probably I can. Okay. But then whether I can build something really general for an arbitrary thing, my answer is that not within the next 2-3 years. I think that we are too early for that. For special classes of non-problems, yes, you probably can build something focused on that. For example, this class of problems, okay, we can build software based on this for this kind of things. But for general, for example, this thing, I show you this class of problems. You try to minimize something and you want to build a general solver for this kind of minimizing this, not at this time. Okay, so down the future, yes, but not in the next 2-3 years. I think that we are still too early. We're still at the learning stage.
All right, thank you.
Thank you. We have another question from Wilfredo Souza. Wilfredo, please ask your question.
Yes.
Can I ask a question?
Yes.
It's Aaron Bental.
Okay.
Jong-Shi, some general remark. One thing, I think non-convexity is much more serious than non-differentiability.
It's not as serious as non-differentiability. Exactly. I probably tend to agree.
The reason is that the mathematics by which we do optimization is infinitesimal calculus. Calculus of small neighborhood. As such, we are very good at locating things where a sufficient condition exists for and use derivative and second derivative and so forth. But if you're looking for a maximum of a function, a global maximum, that's the only interest in this, usually what we want, then you don't have mathematics at all to identify a global maximum.
Well, yes and no, Ronnie, okay.
With non-differentiability, we have still non-smooth analysis. We have second order condition.
Not exactly. I give you a problem.
Not for everything, but for many things.
Yeah, so but I also give you a very simple composite functions. And I ask you to write down the second order conditions. Okay, it's a piecewise quadratic composed with a piecewise quadratic. Try to write down a second order conditions.
Well, there are general second order conditions.
Not because those are not you won't get exactly what you want. Yeah, so I know, so Ronnie, I refer a lot of your work in the book. Okay, so your work on differentiable things, second order conditions, yes, we have that. So you're right. I mean, you're right. We have that. But you know what, Ronnie? I must say this. I start to doubt the local expansion of functions. Okay, I think that we need to look at things a little bit from outside the box. I know exactly what you're saying.
That's exactly my point. What I'm saying, actually, we do have non-smooth analysis, but it's only good for local still for local things.
Yeah, okay, so.
To do with global. For global, we have to think, we don't have mathematics.
I absolutely agree with you. On the other hand, one thing I probably have not said here is that nowadays we are a little bit abandoning a little bit about the global perspective, okay? For example, if you look at this problem here, it really came from an expectation kind of things, right? Because you have this, okay? It really has to do with an expectation problem. And so I think what is more important is not so much as computing the global solution of this, but rather understanding of how a stationary solution to this problem is related to a stationary solution of the problem where this summation becomes the expectation. Okay, so in other words, that in a way that the global aspect of the non-convexity is in a way has been too much emphasized in optimization at the expense of detaching that from what the source problem is, right? So if you look at this, the source problem is that in a way that you have an expectation, okay? And so what you really want to understand is how the suboptimal solutions or stationary solutions of this discretized problems, how that is related to the some kind of solution of the expectation problem. I think that is a question that we have not answered enough. And that actually is contained in one of the chapters, is to try to understand how the computable solution, I guess that's another word that I want to use, is how the computable solutions, okay, what properties they have. If the problem actually comes from an expectation problem, then how is the computable solution of this discretized problem related to a desirable solution of the source problem, which presumably involves expectation? So I would rather ask that question than asking the question whether I can compute a global mean of this problem. So it's a little bit different perspective.
I think still, I mean, there is a good progress in some non-convex problem. I'm working in a current paper that
you should send me, Ronnie. I'd love to see it.
Okay. Yeah, it's.
I love to see it.
Some global ideas about locating a global maximum.
Okay. Okay. Yeah, that would be very, very interesting. But so far, I mean, that we are very much taking a local perspective. Well, not so local, but then going back to the source, right? So as I said, I'm less interested in the global solution of this problem, but rather I will be interested.
But normally we have serious problem that you have to maximize the non-convex problem.
I know.
Algorithm, and if you have an algorithm that you can find an upper and lower bound and are tight, then you solve the problem.
Yeah, but then, I mean, for particular problems, you probably can. For example, for that problem, we know that there are only finitely many stationary values. So if there's a way to find all these stationary values, we're okay. There are only finitely many, but it could take us.
Stationary values that are local minimum or also local maximum?
No, I mean, they must be. One of them must be the global, right?
Right.
Station value, one of them must be the global.
How do you know that you generated all of them?
Okay. A very good question. Of course, that's I don't, right?
Yes, yeah, so thank you very much for the nice discussion. So
yeah, I know, but then yeah. See, this is very general K1, K2, right? So if you give me sort of small number of pieces, maybe I can do that. I mean, there's combinatorial, the combinatorial properties here, right? So I could enumerate, for example. I could enumerate. So one way to find the global is to enumerate. Now, so somewhere along the line, combinatorial discreteness and continuous, they have to merge. I can get the global problem solution of this by enumerating the different pieces. Okay, so I could do that. Whether I'm willing to do that, I don't know, right? So at least for certain, yeah.
Then you are going to the era of neural networks and things like that. It's not far from that if you start to enumerate.
Yeah, I know, but that's for the ML people to say. I know that there's a lot going on already known about non-problems, but I guess I do want to emphasize the fact that when you have these two properties coupled, and that's where all the trouble begins.
I think your talk and your book will actually influence many people.
Yeah, and also probably raise a lot of controversies.
Yeah, which is very good. Which is very good, Jong-Shi. Okay. So let us answer two more questions, yeah, and then come to an end. So Wei Wang is asking if the problem which we see now is
which is what?
The problem we have now on the slide. So the piecewise affine regression problem. If this is a DC programming problem, this is for the first question.
Okay. In principle, yes. Okay. But then to find the DC decomposition may not be beneficial. Okay. So my answer is that if you just ask the question whether this is a DC function, my answer is yes. Okay, it's probably yes. Okay, because you have the general result that says composition of DC functions is DC. Okay, so my answer probably will be yes. However,
yeah, there is a second question, Jong-Shi. So the question is if you can obtain the global solutions.
Oh, for this one, we just discussed this with Randy, right? So if you want, you can always enumerate.
Yes.
Okay, but then short of the enumeration, I think that would be that requires some other ways of thinking.
Great. Yeah. And Wilfredo Souza is insisting on parametric versus non-parametric models, and he's asking why we do not non-parametric models. I'm not sure.
Okay, so let me show you something. Okay, so this is the reason why you want to look at this. We do have this chapter on low randomness, and this is the ship constraint index models, okay, or rank constraint. These are non-parametric estimation problems, okay. These are non-parametric. So if it's familiar with so-called the convex regression problem, okay, and so that's a non-parametric problem. So we do have non-parametric problems, and some non-parametric problems can be formulated as parametric problems. But of course, there are many, because in general, non-parametric requires infinite dimensional optimization. And I'm a total novice, okay, about infinite dimensional things. And so, but then we do have, so for this class of problems, they are non-parametric in nature, but they can be formulated as parametric problems.
Great. Okay. Then I propose to stop here.
Thank you.
So, okay. Thank you, everyone.
So we had today more than 400 participants. Yeah?
Oh, okay.
So this was the right place to present your book. So thank you for the nice talk. I just want to announce the participants that we will post the slides and the video on the website of our seminar, and that the speaker next week will be Adrian Lewis. So
another great speaker.
Have a nice week indeed.
Thank you.
And stay safe. Thank you, Jong-Shi.
Yeah,
nice
stay safe.
Nice
everyone. Thank you.
Bye-bye.
Bye-bye. Bye-bye.